Hello everyone, I'm Yashwant Yogi and today we are discussing about the recitation for week 16. So we will move on without wasting any time to question number 1. So the question says polonium is the only element with crystal structure based on simple cubic unit cells. So the important information we have, we will mark it down. Polonium and simple cubic unit cell. If its density is 9.142 grams per centimeter cube, and calculate an approximate atomic radius for polonium. So we have to find the R. So here, as you see, we have the diagram for a simple cubic unit cell, and you can see how the atoms are arranged here. You can see that at each corner there is an atom. So if you see something like this, there's an atom here, an atom on the each corner, and of each atom 1/8 part is included in this cubic cell. Okay, so if we count the number of atoms, resultant atoms inside a simple cubic unit cell would be, there are 8 such corners, and on each corner we have 1/8 part of an full atom, sorry. So the resultant is 1 atom per unit cell. This is for simple cubic unit cell. Okay, so we know that right now, and other information, as you know, we already know that the density I represented with rho, and the element is polonium. So if you check polonium, it's represented by PO, and its atomic mass is 209 AMU. Okay, so we know this much information, and now with this information we need to find the atomic radius for polonium. Okay, so goal is to find the R, or here it's small r. Okay, so let's move on. We know the density. So what is the density? Density is represented as mass upon volume. Okay, so we know the density. We can find the mass using the mass. As we know, there is one atom in this UN unit cell. So if we find the mass of one polonium atom, we'll know the mass included in this one unit cell. So we can find this mass, and we don't have it right now, but we can find it. And talking about the volume, so this volume can be represented as something as a cube, where a is the side. Okay, so what we need to do is we need to first find the mass, and then we will find the side a using both the values, and from a we will get the radius. So here a equal to 2r. So let's go on. Let's start with the mass calculation. So as you know, 209 AMU is the mass of one atom of polonium. So that would be so I would write it down: one atom of polonium, 209 AMU. That is also mass of one unit cell, because we know that one unit cell contains one atom. Okay, so we know that already. So let's go on now. To find this density, it's in grams per centimeter cube, but what we have here is in AMU. So we need to convert this AMU into something that relates to gram and centimeter cube. So what we'll do is we'll convert AMU into grams. So we know that 1 AMU is equal to 1.66054 into 10 raised to minus 24 grams per AMU. Okay, so either I would write it as just grams. Okay, so now I will do that. Therefore mass of unit cell would be 209 into 1.66054 into 10 raised to minus 24. 209 was in AMU, this is in grams per AMU. So AMU get cancelled, and what we have is 3.470526 5 into 10 raised to minus 22. Okay, let's separate this down. Grams. So this is the mass of 1 unit cell. Now we'll substitute that and find the volume in this equation. So what we have, I will convert it down. So volume becomes mass upon density. I substitute the mass to, and then I put the density from above. This is in grams, so it's 142 grams per centimeter cube. Grams are cancel, and what we have is 3.796244 or 21 into 10 raised to minus 23 centimeter cube. So this is the volume. Now from volume, as I said, we know that the volume is equal to side cube, that is a cube. So now I will try to find v equal to a cube equal to this value. Therefore a is equal to cube root of this value. So 3.7962 1 by 3. So what you will have is something as 3.3608 into 10 raised to minus 8 centimeter. So this unit was centimeter cube, so when we take a cube root, it becomes centimeter. This is the side A. Now we know that A is equal to 2R, therefore R is equal to A by 2. So now when you substitute this value here, you will get R equal to 1.6804 into 10 raised to minus 8 centimeter, or since the limitation of digits, we will write it down as 1.68 into 10 raised to minus 8 centimeter. So that's your radius. You can write it as R or R, and that's what you get, 1.68 into 10 raised to minus 8. So moving further to question number 2. Okay, now we'll read. It said one crystalline form of iron has density, again you know the density, that's rho, and a cubic unit cell length of this much, 0.286 nanometers. So that's the A, the side length. How many iron atoms are in unit cell? So you have to find the number of atoms in the unit cell. So we'll note down what information we have. So we have rho equal to 7.93 grams per centimeter cube. We have the side length as 286 nanometer. That is also equal to, I can write down it as, like, nanometer is 10 raised to minus 9 meters. So I can write down as 286 into 10 raised to minus 9 meters, or better it would be if I do it something like 0.286 into 10 raised to minus centimeter. I'm doing it in centimeter because the density here is in centimeter, so it will make it easier. Okay, this doesn't look like centimeter. Now it looks. So what other information can we get? So to get the mass of the unit cell, we also need to know the atomic mass of iron, right? So the atomic mass of iron from the periodic table, you will get of iron, or Fe, is equal to 55.84 AMU. Now again we will use the same factor and we'll convert it into something that is more of a in form of grams. So what we can do is we will again multiply this with 1.66054 into 10 raised to minus 24 grams per AMU, and we get 9.27328563 to 10 raised to minus 23 grams. So now we have the atomic mass of iron in form of grams. Okay, so we have the basic information. Now from this unit cell length A, we can find the volume, right? So understanding the logic of this question is, your goal is to find number of atoms in unit cell. That's your goal. Okay, so you want to reach find the number of atoms in unit cell. To know that, what you need to do is you should know what is the mass of that unit cell. Okay, so once you know, here you go, density, mass upon volume. So if we already know the density, we can find the volume from the A, that is A cube. And once we know the mass of the unit cell, we can try to find out the number of atoms in the unit cell, because mass of unit cell would be equal to mass of Fe atom, that is iron atom, multiplied by the number of atoms in the unit cell. So if you find the mass here, we will get this. We already know the mass of the iron, that is this, and then we can get this, okay, number of atoms. So let's put some values here. Okay, let's do step by step. We'll put the density 7.93 grams per centimeter cube. You have mass, let's keep it as it is. Volume would be A cube, so it is 0.286 into 10 raised to minus 7 centimeter cube. And using this, you will get M equal to so doing this calculation, and you should get something of mass of the cell as 1.855116921 into 10 raised to minus 22 grams. Okay, now we will substitute this here, and we already know the mass of the atom of the iron atom, that's here, and now we can find the number of atoms. So substituting, therefore 1.855116921 minus 22 grams equal to mass of atom iron, you get 9.27328563 minus 23 grams, and number of atoms. So what you get is the number of atoms, number of atoms is equal to 2.000, something like that. So we can say there are 2 atoms in an unit cell. So the next question itself will give you an idea what this unit cell would look like. So the body center cubic lattice, that is the body center unit cell, has total 2 atoms overall. So let's change the color. Here you can see it's 1/8 on each side. So there is something as, now I'm directly moving to the third question, but I'm just trying to show that if there are 2 atoms in a unit cell, that means it's a BCC structure, that is body center cubic lattice, that is body center unit cell. How? 1/8 on each side, so 1/8 into 8, and 1 in the center. You can see this one, the big one, center. So plus 1 in the center, you get 2. So that is for BCC. So the structure here originally, if someone asks beyond this thing, other than how many iron atoms are in unit cell, and then someone asks you what kind of unit cell it is, then you can say it's a BCC structure, or body center unit cell. So moving to question number 3. So reading the question, barium crystallizes with body center, so you know it's a BC structure, or I call it BCC, body center cubic lattice, with a edge of A equal to 502.5. And what is the radius? So we have to, radius is asked here. Okay, so I'll first rub around this. Let's know that how would you find the radius, because in the previous ones here the atoms were connected to each other. Here you can see, wait, I'll change the color. You can see the atoms are touched, so you can just write A equal to 2R. But the same thing is not here, because you have put one more atom in the center. There's some gap here, so you have to find the radius and the unit length value from some other way. So if you see here, these values are given, and you will notice that the D, that is the body diagonal, the diagonal that passes from one corner to the opposite corner of the unit cell value is equal to 4r. Okay, so it's like 1/8. Wait, it's like 1/8 till here, and like the r here, and then it's 2r, 2r here, and then it's r again here. So you can directly understand, even if you don't do this calculation, you can understand that D, that is the body diagonal, is equal to 4r. Okay, so if we get this D, we can get this r. Okay, so let's do it. And we also know, since A is given, we have to find a relation between D and A, and that's this. Okay, so the values for body hypotenuse, that is D is equal to under root 3a, that you directly get from here. You can calculate it here by yourself. The steps are given. Since the C is the diagonal of B and A and B are both equal, so it will become 2a square. Then using this as the side, the C as the side, and this as a side, you can calculate the body diagonal, that is C square plus A square will give you 3a square, and that's how you get the relation. So you have D equal to root 3a, so you can calculate that. Root 3 into 502 picometer, that is 8702.3555308 picometer. So 1 picometer is equal to 10 raised to minus 12 meters. I'm not converting it because at the end our goal is to find the radius, so I can write the radius in terms of picometer. Now we also know we got the D. Now we also know that D is equal to 4r. So from here we can get D by 4 is equal to r, and you substitute the value divided by 4 and you get approximately 217.588 picometer, that is 218 picometer. So you get your radius of Ba atom. Moving to next question. We have solved the value that was asked for. Now moving to the next question, that is question number 4. So aluminum crystallizes in face-centered cubic lattice. So we have now face-centered, so FCC. If the edge of the unit cell is A equal to 405 pm, okay, again picometer, then what is the radius of Al atom? Again you have to find the same thing, so it's something similar. Okay, so what we can do, again you have to understand the relationship between the corners and this the lengths. Okay, so the difference between a BCC and an FCC is that a BCC there's an atom in the center, okay, but in FCC there's an atom on the face edge, so that's what it's called as face centered. Okay, so if you see this structure, you can understand that the diagonal, this diagonal is equivalent to 4r, that 4 times the radius. Okay, so we can use, if we can find this D, we can find the radius. So first, to find this D, we need to find its relationship with this A, that is 405, and here it's already given, but if you want you can do something like direct calculation. So I can show you, but I think that there's no need for that. So let's, the relationship between D is equal to D square is equal to 2a square. How did I get it? It's an hypotenuse, the side, so D square is equal to a square plus a square, the Pythagoras theorem kind of thing. So what we have is D is equal to root 2a, and once you solve this, okay, so here they have used a C as the term, so you don't need to worry about that. The D and C here are same, so I'm writing D is equal to root 2 of the A, that is 405 pm, and what you get is 572.756498 picometers. And once you get that, you know that the D is equal to 4R. So again R equal to D by 4, and what you get is 143.18912 picometers. So yeah, that's the way we do it. So if you understand the relationship between the lengths, you will get it easily. Moving to the next element, and oh, I think the questions are missing. I will write down the questions. So it is, the first A part is 2008, B is 59, CO 27, and the third part is 9, Li 3. So what we need to do is we need to find which nuclide would you predict to be stable and why. Okay, so you can refer to this chart that is here on page number 1114, and you can try to understand which one would be stable and which would not be. Okay, so what you can do is, to check the stability, you need to find the ratio of your neutrons and your protons. So let's check in the terms of oxygen. So how many protons do we have? That is the atomic number, that's 8. So you have 8. Now to check the neutrons, you will subtract the atomic mass. I'm writing it in detail here for the first one, then you can just do it fast. Upon, we have the protons, so we have around 12, so it's like 20 minus 8, you get 12. So the ratio neutrons upon proton is 12 by 8, and that's 1.5. So if you check properly here, that up to neon you have a ratio of neutrons per ton proton of 1.0 normally. So what does that show is that our ratio is higher, which means that there are too many of neutrons, making it unstable. So our result will be unstable, too many neutrons. You can understand this when you compare it to something in your periodic table. So if you see something in your periodic table, here we don't have the atomic mass, but normally oxygen has around 1608. So like 20 is too far from 16. That shows there are too much of neutrons. Okay, now moving on to cobalt, that is 5927. Again we will do the same thing. Then by Z would be 59 minus 27, that is atomic mass minus the protons and the protons. So that comes out to be around 1.1851. So moving close where it is, so if you see at Fe it's 56 by 26, so it's beyond Fe, and there it's N by Z is 1.15, so it will be close to this. So and the values here are also close to 1.15, so we can say, wait a minute, okay, it's stable. If you check this with the atomic mass of cobalt, you will find that it's very close to 59, so that's, we can say it's stable. So moving next to Li, that is lithium, we'll do again the same thing. It was Z, again Z, we have 9 by 3 by 3, you have 6 by 3, that is around 2, and that's too much high. If you know already that we did near neon, it should be around 1, but it's like 2. Also you know that lithium has 7, it's 6.9 something, I'm considering it 7 atomic mass in general, so it's too far away, so we can write it's unstable, too many neutrons. So we have only cobalt as stable and other two as unstable because of too many neutrons. Moving to the next question. So this is kind of a revision of the previous classes. So let's move on. Arrange each set in the order of increasing atomic size. So atomic size, let's find where these atoms are placed first. So rubidium, that is, let's change the color, it's somewhere here. Then we have K, then we have CS, cesium. So we have to compare this in atomic size. We generally know that the atomic size increases as we go down the group. Why? Because you know, as you go down the group, there's one more orbit added to, so considering this is K, that is 19 in the fourth group, so it will have around let's make 4. So this is a rough diagram, don't take it that way. 4, and then if you add rubidium, there will be one more orbit around it, so that will increase its size. Okay, so I will rub this now. Okay, in that way what we can say is that K would be smaller than rubidium, that is Rb, and Rb will be smaller than cesium. So what we can write is K is the smallest, then we have the rubidium, then we have the cesium. Okay, that's how the size vary. Now taking to the next one, Co and Be, that is Co and Be. Here the trend, if you remember, it's something like as you go in this way, that is towards the right side, the size decreases. Why? So it's in the second group, right? So let's make it much better diagram. This is the nucleus. Okay, then you have the first orbit and you have the second orbit. So we have beryllium, which has 2 electrons in the outermost shell, that is second shell. Now when you want to go to carbon, you add 2 more electrons in the same shell. You are not increasing the orbit, you are having the same shell for which you are adding the atom, but at the same time there are 2 extra protons that are added in the center, so they can pull this more strongly. Okay, and that's why the size decreases as you go down the right side. Okay, you move towards right. So why is this happening is that if you add one more orbit, the inner electrons try to kind of create a cover up for the outer ones. Okay, so whatever, if even if the protons are increasing like 3, 4 or 5, its effect will be mostly covered by the inner ones, and the effect decreases on the outer one. That's why if you go down the group, the atomic size increases, but if you add the electrons in the same orbit, the size decreases. Okay, so what we will have is Be is smaller than carbon is smaller than, sorry, I did it opposite. It's oxygen that is smaller than carbon, smaller than Be. Okay, so moving to next question. Arrange each set in terms of ionization energy. First, ionization energy. The term first is important, and let's revising what ionization energy means. It's the energy required to remove first electron from the valence orbit of the atom. Okay, so you have to provide some energy to remove the electron. So the ionization energy shows how much energy you had to give. So let's note down where these atoms are: Sr, Ca and Ba. So Sr, Ca and Ba. Okay, so we remember that as from the previous question itself, that the atomic size increases, right? So I'm giving you the reason why whatever the ionization energy vary increases. So if the atomic size increases, there are more electrons added in the outer shell. Okay, because of that, the atom becomes less like, it's okay for that atom, it doesn't matter for him if one electron is lost. So this barium would be less concerned about losing an electron than the calcium. Okay, and plus since the electrons are closer to calcium, the valence electrons are closer to calcium, it will have higher control over them. whereas for barium they are like 2 extra orbits away, so it has less control. So what you can say, that the ionization energy is highest for, like I can show you the trend itself, that as you go down the group, ionization energy decreases. Okay, so it will be easier to remove electron from barium compared to calcium. So the energy required to remove the electron will be higher for calcium. So we can write that calcium, oh it's asking in order of increasing. Okay, so I'll write from the lowest to the highest. So barium will have the lowest, then Sr, and then calcium. Now let's go on with Nb and Ne. So Ne, that is neon, boron, and I think it's nitrogen. Okay, so as you see, neon is already a inert gas. It's all orbits are full filled. Okay, it's stable, it doesn't need an electron, it doesn't want to give an electron. Okay, and you also know that fluorine, I'm just comparing the trend. Okay, so the fluorine needs one atom to get stable. It's just one atom, so if he gets that one atom, it will become stable. So it won't let others to take away its electron, because it wants an electron and not wants to give away the electron. Whereas if you compared lithium here, like I'm just showing the trend, if it gives away that one electron, it will be more stable, so it will give away this electron more easily. Okay, so what we can say is the ionization energy increases as we go right side. Okay, so we will have B, then it's N, and then it's neon. So the lowest ionization energy would be for boron, then nitrogen, and then neon. Okay, moving to the next question. Circle the appropriate trend for each property. So it's more about understanding the trends. Okay, so half of the trends we have already studied in the previous question. So as you go down the periodic table, atomic size, you saw this, atomic size increases as you go down the group. Okay, so we'll write increases. Okay, that's the answer. As you go to the right of the periodic table, atomic size decreases, so we'll do size decreases. So if someone is listening to this question directly, please refer to question number 6 and 7 for reference. Okay, as you go up the periodic table, ionization energy. So here we found as we go down the table, ionization decreases. So we can say if we go up the group, it's increasing. So we'll do increases. Okay. Now as you go left to the periodic table, electron affinity. So now this is a new term, we haven't discussed it yet. So electron affinity is like the love for the electron, how eagerly you want an electron. Okay, so we know that, just like you don't need to worry about what's happening here, like in the center. Even if you know just this thing and these two edges, you will understand the trends easily. Okay, so I will rub this in the center. So taking electron affinity, that is love for electron. Okay, how eager that atom is to get an electron. So you know that fluorine is very eager to get an electron, because it will get into a stable position if it's gets one electron, whereas lithium is least concerned about getting an electron, it wants to give that electron. So the electron affinity of fluorine is much higher compared to lithium. So what we can say is, as you go down or like to the right side, the electron affinity, I'm writing it as Ea, increases. Okay, don't get confused with neon here, because neon doesn't want electrons, so its electron affinity is like null, so it doesn't want an electron, so be careful with that. So you go down right side, Ea increases, but the question asks as you go to the left, so it's in opposite direction, that means the Ea decreases, so we'll write decreases. Now next question, as you go to the right of the periodic table, metallic behavior. So we know metallic metallic nature means it's ready to give away electron. Okay, there are lots of electron give away electron, so it's kind of opposite to the electron affinity thing. So the trend would be nearly opposite. So as you go to the right, the metallic nature decreases. It will be totally opposite to this electron affinity behavior. So Na, lithium are more metallic compared to F, because F is non F fluorine is definitely a non-metal. You can see the trends, that this line separates metals and non-metals. So these are non-metals and these are metals. Okay, so what we can say is, as you go to the right, the periodic table metallic behavior decreases. Next, as you go down the periodic table, the acidity of oxides. So acidity is something related to more of like an electron affinity kind of thing, and you know that more metallic, more basic it will be, the oxide will be, as well. Other than that, quite opposite to that, if it's less metallic or like nearly no metallic, the acidic oxide nature increases. So to the left side, what you will get is more of a basic oxides, whereas on the right side you will get more of a acidic oxide. As well as you go down the periodic table, the basicity increases, like it's more metallic, right? The francium would be more metallic than lithium, that's why it will be become more basic. Okay, now it's asking about acidic, so if it's more basic, it's least acidic, right? So we can say that as you go down the group, the acidity of the oxides decreases. Moving to the next question, as you go to the left of the periodic table, the ionization energy, so it's similarly opposite to that, we did it already. As you go to the left, the ionization increases as we go to the right. So as we move to the left, it decreases, so we will write it decreases. Okay. These trends are easy to understand. You just need to do is you just note down the elements on the left and the right, and then you just compare them, like you know the properties already, and if you compare, you can find out the trends without even remembering them. Okay, so moving to the next question. So here it's asked about the intermolecular forces. Okay, what is likely to be the strongest intermolecular forces between the following molecules? So other than iron, so beyond this it's iron, and that's the strongest, you know, like plus minus. So beyond that, the intermolecular forces, it's like a shake hand kind of thing. The intermolecular forces, they don't form a bond, it's like a relation they have just. So the strongest is iron dipole, so it's iron and there's a dipole. Okay, and then it's hydrogen bond, dipole dipole. So what does a dipole mean? So if there's a like highly electronegative element like oxygen, and it's connected to hydrogen, so this is more electronegative oxygen, right? So it will pull its electron, the electron shared between them, towards itself. Okay, so that makes it a dipole, the sign. Okay, that's what it is here. So dipole dipole, then iron dipole. So it's induced dipole, this is induced dipole. So what does induced dipole mean? Okay, so let me show you what does induced dipole mean. A dipole affecting another normal thing to create a dipole. So let's consider this is again another H, and we have a C. Okay, so this is a dipole, like this one is a dipole, and here is an hydrogen. So what happens is that hydrogen would be attracted, like sorry, wait. Okay, so this dipole induces the dipole in this, and because of that, what happens is again this is like kind of positively charged, and this becomes kind of negatively charged, and again it creates a dipole. Like this dipole is induced by this one, so this causes a induced dipole here. And the next one is the induced dipole creating another induced dipole. So like again the next H and C will create an induced dipole, so that will be even less stronger. Okay, now let's rub this. Okay, sorry, moving to the questions. So I will make the structures so we can understand what's happening. So first we have hexane. So making a structure, it's 1 2 3 4 2 3 4 5 6. So it's carbon chain, and I can make it like this. So it's same all the way, carbon H. Okay, and then we have butanol. So butanol has 4 carbons, so let's make it like carbon we have okay, so that's butanol. So what will happen over here is we have a dipole. Where is the dipole? This is the dipole. Let's can see here hexane is not polar, it doesn't have any polar component, it doesn't have any highly electronegative element. But in butanol we have oxygen. So what oxygen does is it creates a dipole. Okay, and this dipole kind of induces a dipole here between these bonds. So and it makes it kind of slightly positive, and then we have a dipole. So it's an induced dipole. Okay, so what we'll have is a dipole induced dipole thing here. So let's write it down. ID stands for induced dipole. Going to the next one, dichloromethane, CH Cl, an acetone, C double bond O, and you have just making it the same way, H, and if you have C, H. So you can see again we have a dipole here. Okay, oxygen is highly electronegative. At the same time we also have a dipole here because chlorine is highly electronegative. So we can say what it's causing is a connection between them is more of a dipole. So we have you should remember that we are asked the strongest. Okay, so this will create and at the place is a induced dipole. So the chlorine will cause a induced dipole over here. Okay, but what is asked is the strongest intermolecular force, and we know that dipole is much stronger than dipole induced dipole. Okay, so what we will do is we will just mention the strongest. So that's why we have written dipole. Okay, next we go is methanol, C H and O H. Okay, and then we have H, oxygen. Okay, let's make it this way so it shows easily. Oxygen, H. Okay, so here what we have, again you can say that it's a dipole directly. Okay, oh, this is dipole, and then this is also dipole, but we have to check first, is there anything stronger than that? So we know there is something called edge bonding. What edge bonding is, if there are two highly electronegative elements and that are directly connected, like can be connected through some other element like hydrogen. So what we can say is here we are having a kind of hydrogen bonding is happening. So what's happening is this is slightly negative, this is slightly positive, and this is again negative. So it's H between two highly electronegative elements. Here same way you will see between this hydrogen. Okay, so here we have hydrogen bonding, so we can write hydrogen bonding. Now you might ask a question, why no hydrogen bonding in question B? So here it's not the chlorine atom or the oxygen atom are not connected to a hydrogen. Okay, they are connected to chlorine and carbon, so we can't have a hydrogen bonding. Okay, so that's why, so it will be hydrogen bonding, and this will be dipole dipole, and this is dipole induced dipole. Okay, moving to the next question. Okay, again I have something missing around here. You note it down. O oxygen, OH oxygen, O chlorine, N and H. This is oxygen, OH, O. So I think there's nothing like you have to just remember this, or but still you can understand it easily. So here there's a C. Okay, like you can understand it's a form of chain. I'm writing it down, it's not written mostly. So it's carboxylic acid. So carboxylic acid. Okay, so how did I know there is a carbon? So it's carbon, carboxylic, oxalic is this O, and it's acid, so this thing can produce an H plus, so that's why it's called carboxylic acid. Okay, next one is an aldehyde. Wait. Okay, so why I'm writing this as aldehyde is because it's related to a chain. Okay, like a round chain, and that's why it's like a C here, and oxygen OH. Next, moving to this one here, we call it, you can call it ester. So there is like C, there's an O, and again there is a C. Okay, there is no OH here. If this oxygen doesn't have an OH, okay, otherwise it will become an aldehyde or carboxylic. So it's ester, or since it's in a ring, you can also call it as lactone. Okay, now next one is, there's a chlorine here, so it's simple as a halogen group. Okay, and so if it's a fluorine, chlorine, bromine, iodine, you can call it an halogen. Next one is we have nitrogen here, so it's simple as an amine. Okay, it has an H here, so we'll write it as an amine. Again, this one is a ketone. There's just a single oxygen with a double bond, so that's where you remember it. Then we have an alcohol, because it's just OH, and there's no, this is carbon H and H, and it's related to OH, so it's called alcohol. So wherever if there is only OH then that's an alcohol. And this again is an ester, so you see this thing, and there's again same kind of bond here and here. The only difference is that this is in a ring and this one is in a simple structure, a linear structure. That's why we can't call it lactone, we call just it ester. Okay, so each one of them can be easily remembered. Yeah, it needs practice, but you can. Okay, I think that's the end of the this recitation for week 16. If you have any other question regarding any of the related questions, you can email me at this email ID. And I think that's all. Thank you for listening. See you next time.